energy transition. We use copper to generate electricity. We use copper to distribute electricity. We use copper to store electricity. So without copper, there is no technology, there is no energy transition. So it's fundamental to the United Nations Sustainable Development Goals. And when we look at pictures such as this one, we're looking here at the porphyry copper deposit at Grasberg, Indonesia, one of the world's largest porphyry copper deposits that also contains a significant amount of gold.
Una conferencia de los pórfidos en Perú, Argentina.
Here we're looking at another one of the world's largest porphyry copper deposits, Chuquicamata in northern Chile. Significant amounts of copper as well as significant amounts of gold.
Tenemos que Australia. Una oportunidad como esta que me dicen, no se nos va a presentar otra vez.
Excuse me, doctor. Yeah.
Yeah, I'm not sure how to do that, to be honest with you, to add you to the moderator.
We could try if we could right click on the names. I think it's gonna appear the option of moderate.
Yeah, I don't. Let me. Okay, I can make you a co-host. So I just made you a co-host.
Thank you very much.
Okay.
Sorry for the inconveniences for.
No, it's okay. It's okay. Okay. So first, let's talk about big picture. Porphyry copper deposits are the world's most important source of copper, 60% of global copper supply. They also co-produce or produce as a byproduct significant amounts of gold, probably 10% of global supply, probably 15% of global silver, and almost all of global molybdenum. So when we see these really large holes in the ground at Grasberg, at Chuquicamata, at Bingham Canyon, the reason that these holes exist is because the rock that we're excavating is extremely enriched in copper. So, for example, at Bingham Canyon, the average ore grade is 0.42% copper. If we compare that to the average concentration of copper in normal continental crust, it's about 0.0027% copper. So the reason that we mine these deposits is they contain truly orders of magnitude more copper than normal continental crust. And in addition, they contain significant amounts of gold relative to normal crustal concentrations. Now, when we look at these big holes in the ground, these porphyry deposits, I have spent most of my career trying to understand how porphyry deposits form, why there are different metal ratios among porphyry deposits. And that's what I'm going to focus on in the next little while for this talk. So if we look at a map here globally of porphyry deposits, all of the deposits in orange, these are the 10 largest porphyry copper deposits in the world. And we can see that 5 of them are in South America. We can see 3 of them are in the United States. We can see in red are the 6 largest gold-rich porphyry copper deposits. So we've got Oyu Tolgoi, we've got Kalmarkir, we've got Grasberg in Indonesia, we've got Cadia. And so we understand very well today that porphyry copper deposits form in active subduction zones. And when we look here at the western margin of western margin of the Americas, we see all of the porphyry deposits forming in active subduction zones. Similarly, around the western margin of the Pacific Ocean and Indonesia and the Philippines, we see porphyry copper deposits forming in active subduction zones. And then in purple, we're looking at porphyry copper deposits that formed in paleo subduction zones. So we know very well that subduction zone environments are required in order for porphyry copper deposits to form. Now, in subduction zone environments, we also have a pretty good understanding of how magmas form. So in a subduction zone environment, for example, the Andean margin off the western coast of South America, we know that we have Pacific Ocean crust and the sediments on top of that crust being subducted beneath South America. And as the sediments and the hydrated ocean crust are being subducted, the water and other volatiles in the sediments and in the hydrated ocean crust, it progressively, at higher temperatures, it devolatilizes or it boils, and that water and volatiles then ascend into the overlying mantle wedge, where they induce melting of the mantle wedge by lowering the solidus temperature at constant temperature and constant pressure. And so when we see volcanism in subduction zone systems, what we're looking at is ultimately the result of this degassing process as the subducting slab and overlying sediments add water plus other volatiles to the mantle. Now, we also know that the water and other volatiles being added to the mantle wedge, it's not a pure water fluid. We know that that fluid is very complex and contains water and CO2. It contains dissolved sulfur, chlorine, and other anions and cations. And so one of the things that I've been really interested in is the connection of shallow level magmatic features, such as porphyry copper deposits, and processes that happen in the deep crust and the subarc mantle. Now, in subduction zone environments, this is also very common. Now, this is subduction zone magmatism. So we're looking here at a volcanic eruption in a subduction zone environment. And I want to highlight a couple of things that are relevant for our understanding of porphyry copper deposits. If we look at the volcano as it erupts, what I want you to look at above the volcano is all of the white clouds. So prior to the volcanic eruption, notice where all of the clouds are, and all of the clouds are stationary. They are not moving. But watch what happens to the clouds as soon as the volcano erupts. We can see the clouds are moving. And the reason that the clouds move is because when all of this mass, this volcanic ash is erupted into Earth's lower atmosphere, it sends out a tremendous shock wave energy in all directions through the atmosphere. And it's the shock wave that is moving ahead of the ash itself. And that shock wave physically pushes the clouds to higher levels of the atmosphere. And that shock wave, as the captain of the boat indicates, can be heard by everybody on the ship. So that shock wave is really important, and I'll come back to that. So if you were to go to the top of an active volcano and you were to look inside the volcano crater prior to the eruption, this is what you would see, the video on the right. So here what I'm showing you is a video that I took where I'm looking down into an active volcanic crater, and we can see all of the yellow here is sulfur that's sublimating or precipitating as native sulfur. And that sulfur is precipitating as native sulfur from these magmatic hydrothermal fluids that are discharging from a magma chamber at depth. And on the lower left, we can see one image here in the center showing one of these fumaroles with the native sulfur crystals around the margins of the fumarole. And then on the lower left, I'm holding a sample near one of these fumaroles where what you can see are all of the minerals here that are characteristic for porphyry copper deposits. We have minerals, for example, pyrite and chalcopyrite and bornite and pyrite, galena, sphalerite. So what we're seeing in real time in one volcanic crater is these fumaroles are discharging not only sulfur, but the fumaroles are discharging all of the metals that complex or bond with sulfur to precipitate as these metal sulfides. So we have spent a lot of effort in the economic geology community over the last 100 plus years to understand how these eruptions and these volcanic discharges relate to the formation of mineral deposits. Here is a volcanic eruption in Japan. And just again to highlight that what we're looking at here is we're looking at ash that was previously part of a magma chamber beneath the volcanic edifice. All of this ash, it contains every element in the periodic table, including copper, gold, silver, molybdenum, rhenium, tellurium, platinum group metals. All of the metals that we find and we mine in porphyry deposits are being erupted as part of this ash plume. So we understand really well the dynamics that cause the eruption of these ash plumes. And if we look at the details of what caused volcanoes to erupt, on the top left, we've got the volcano, and beneath it, I have schematically shown a magma chamber. So we know that the ash that erupts from a volcano, all of that ash originates in a magma chamber beneath the volcanic edifice. And within the magma chamber beneath the volcanic edifice, what causes the magma to erupt are these blue circles here that represent volatiles or bubbles, bubbles of water plus carbon dioxide. And these bubbles that contain water and carbon dioxide, the water and carbon dioxide is initially dissolved within the silicate melt. And at shallow crustal levels, as the silicate melt crystallizes, so it transitions from a liquid to a liquid plus solids, the concentration of water and CO2 in the melt increase until the melt reaches saturation with water and CO2. And it then exsolves bubbles that are a mixture of water and carbon dioxide and every element in the periodic table. And what we see here in the animation on the right is within the magma chamber, if the blue represent crystals, then what we find is that as the melt progressively crystallizes, it will reach saturation with a water plus carbon dioxide fluid phase, and the fluid will exist as these bubbles or spheres that will ascend towards the top of the magma chamber because the bubbles have a density that is less than the surrounding magma. So again, we understand relatively well how this process works to produce volcanic eruptions. Now, what's important for the formation of for a volcanic eruption is that within the magma chamber, when these bubbles ascend, the bubbles will start as small bubbles when they're at deep levels of the magma chamber. And as the bubbles rise towards the top, the lithostatic pressure on the bubbles decreases. And as a result, the bubbles will grow in volume. And so I'm showing that here on the right by this balloon that's inflating. And the balloon is inflating because it's held within a vacuum chamber. And all that I'm doing here is removing air from the vacuum chamber, so simulating decompression. So these bubbles of water plus CO2, what we commonly think of as a magmatic hydrothermal fluid, as those bubbles ascend from the bottom to the top of a magma chamber, their volume increases. Now, what's important is that the overall volume of the magma chamber remains constant. So what happens during this process is we have a magma chamber that has a fixed volume, and as the silicate melt crystallizes, there is a small volume change, a negative volume change associated with the transition from liquid to crystals. And degassing, or the exsolution of a water plus CO2 volatile phase, that volatile phase, its volume increases. And what this does is these bubbles exert pressure outward on the magma. So pressure is force divided by area. And so these bubbles within the magma chamber, as the bubbles accumulate in the upper apical portions of the magma chamber, these bubbles can have pressures on the order of 2,000 bars. And for a magma chamber that's 4 kilometers deep, the lithostatic pressure is 1,000 bars. So the bubbles, hold on one second. The bubbles exert a pressure that is twice the lithostatic pressure. So the exsolution of these magmatic hydrothermal water plus CO2 bubbles, they increase the overall volume of the magma because they're pushing out on the magma. And as a result, the magma responds by erupting. And this is the eruption of a bottle of champagne. The reason a bottle of champagne erupts is that inside the bottle, carbon dioxide is present, and the pressure inside the bottle is about 5 times atmospheric pressure. So there's a really significant pressure gradient between the bubbles of carbon dioxide in the bottle and the air outside of the bottle. Exactly the same as a magma, where the bubbles of water plus CO2 in the magma, they produce a much greater pressure within the magma relative to the pressure of the lithostatic rock or the lithostatic load above. So this results in the eruption. So we have had many studies of this process over the last 100 plus years. So we understand really well the physics of degassing of magma chambers and how that produces volcanic eruptions. Porphyry deposits are simply the volume of rock between the top of an erupting magma chamber and the volcanic edifice. So if we think about porphyry deposits, I'm showing here the general outline for a porphyry deposit. And this is for the Bingham Canyon porphyry deposit in the western United States, where the red outline is the 0.35 weight percent copper shell, and the green outline is the 0.7 weight percent copper shell. And when we look at porphyry copper deposits, they form above an erupting magma chamber beneath a stratovolcano. And we understand really well now that the reason porphyry copper deposits form is that a magma chamber will have erupted many times, producing a stratovolcano. And when the stratovolcano reaches a specific or a certain thickness, so in this case, prior to the eruption that formed the Bingham Canyon porphyry copper deposit, the Bingham stratovolcano was about 4,000 meters above sea level, and the porphyry deposit formed at about 2,000 meters above sea level. So there's about 2,000 meters or 2 kilometers of rock that would have been the lithostatic load on top of the area where the porphyry copper deposit formed. And when we look at the porphyry copper deposit, it forms because of the eruption of a magmatic hydrothermal fluid. And that fluid, as it erupts, if it does not make it all the way to the surface and it gets trapped between the magma chamber and the volcanic edifice, that instantaneous eruption where pressure goes from 2 kilobars rapidly to 1 kilobar and temperature decreases, that results in the precipitation of copper sulfides. And the shock wave that we heard earlier, we see that manifest in porphyry copper deposits in stockwork veining. So the photograph on the left is a pretty typical porphyry copper texture where all of the white and the gray veins here, these are all veins that consist of quartz plus copper sulfides plus molybdenum sulfide. And these veins form as the result of the shock wave during eruption. So the eruption of the magmatic hydrothermal fluid, it will send a shock wave into the rock over the magma chamber, and that shock wave will create fractures that become permeable pathways for the magmatic hydrothermal fluid to ascend. And as that fluid ascends along the fractures that it created or around brecciated rocks that it also can create, then the decrease in pressure and temperature and reaction with minerals on either side of the fracture causes precipitation of quartz plus metal sulfides. And then on the right, we have a very classic, what we call a paint vein, where we're looking here at bornite and chalcopyrite from a porphyry copper gold molybdenum deposit. This is dominated by chalcopyrite and bornite. And all of the copper, iron, and sulfur that's now in chalcopyrite and bornite originated in the silicate melt beneath the porphyry system. And we've spent a lot of time in many porphyry deposits around the world understanding the sequence of events that ultimately lead to the formation of a porphyry deposit. And what we know in porphyry systems is that there are multiple eruptions of fluid. And we see the multiple eruptions of fluid because in this case, for one porphyry hand sample, we can reconstruct events 1, 2, 3, 4, 5, and 6. So we can simply by using cross-cutting features here, spatial relationships, we can reconstruct at least 6 fluid events that impacted this specific volume of rock that we now call a porphyry copper deposit. So what I've spent a lot of my career trying to understand is if we know that the metals in a porphyry copper deposit originated in a silicate magma, we know that porphyry copper deposits, they evolve from intermediate to felsic silicate magmas with compositions that are roughly dacitic in terms of silica, sodium, potassium, aluminum contents. And in these dacitic magmas, the concentration of copper, molybdenum, silver, and gold is low. So copper concentration is on the order of 28 parts per million. And in the porphyry environment, within tens to hundreds of meters above the magma chamber from which the magmatic hydrothermal ore fluid erupted, the copper concentration is 5,000 parts per million. So that means that nature has increased the concentration of copper by a factor of about 200. And similarly, if we look at the concentrations of molybdenum and gold and silver in a silicate magma and compare that to the concentrations of molybdenum and silver and gold in a porphyry deposit, we see that nature has increased the concentration of all of these metals by factors of several hundred to several thousand. And so one of the things that's important for the formation of porphyry copper deposits is that all of these bubbles are forming in a large volume of magma. These bubbles ascend to the upper apical portions of the magma chamber. And then when the bubbles cause the eruption, that eruption is localized in a very small diameter plume where the magmatic hydrothermal fluid ascends. So I've been really interested, and I've done a lot of experimental work trying to understand how the composition of magmatic hydrothermal fluids influences the copper, gold, silver, and molybdenum concentrations and ratios, tenors in porphyry deposits. So if we look at porphyry deposits globally, I've got two maps here. On the left is a map where we can look at major gold deposits in provinces in the Americas. So here what we're looking at are the red areas are gold belts. The red circles are gold deposits. And if we compare that to the map on the right is again showing in orange supergiant porphyry copper deposits with or without economic gold. And in blue, we're looking at giant porphyry copper deposits. And so if we compare the location of major gold deposits in provinces to major copper plus or minus gold deposits, we see that there is some overlap, but not always. So over the last few years, I've spent a lot of time trying to understand this. If we look at the copper and gold contents in porphyry systems globally, where we've got copper on the y-axis and gold on the x-axis, this is the range of copper and gold in global porphyry copper deposits. And we can see some of the world's large, giant porphyry copper deposits, Chuquicamata, El Teniente, Coloquasi, and Los Pelambres. Each of those are here. And then we see giant porphyry copper gold deposits, Oyu Tolgoi, Grasberg, far southeast, Bajo in Argentina, Batu Hijau. And what we can see is these deposits on the left and these deposits on the right, they're all economic for copper. And the copper concentrations among all of these deposits globally are generally between about 0.1 weight% copper and about 1 weight% copper. So about an order of magnitude or a factor of 10 difference. But generally, they have a relatively narrow range of copper concentrations. But gold contents vary pretty significantly. So these giant porphyry copper deposits on the left, they have gold concentrations on or about 0.01 ppm gold, whereas these giant porphyry copper gold deposits on the right, they have gold concentrations that are approaching 1 part per million. So this is a factor of 100 change from here to here. So the copper concentrations are relatively similar within a very narrow range, less than a factor of 10, but the gold concentrations vary by a factor of 100. And then we have these deposits. So these are deposits in the Maricunga Belt in northern Chile in the high Andes, and these are porphyry gold deposits. So these deposits here, Pancho, Lobo, Marte, and Verde, these are deposits that have gold concentrations of about 1 part per million, or in the case of Lobo and Marte, 2 and even approaching 3 parts per million gold. Cerro Casale is about 1 part per million gold and about 0.2 ppm copper. But all of these deposits, these are porphyry gold deposits. They're not porphyry copper deposits. They have a very similar history, but what is distinct is that these deposits do not contain economic copper concentrations, whereas these deposits contain economic copper and they contain significant and economic gold concentrations. So I've spent the last few years working with Jose Tomás Ovalle, who is Chilean. He did his undergrad at the Universidad de Atacama, his PhD at the Universidad de Chile, and a postdoc with me here in Michigan. And he's now a professor at Universidad Mayor. And Jose Tomas has led a project focused on the gold deposits in the Maricunga Belt. And what we're trying to understand in this research project is that if we look at the porphyry gold deposits in the Maricunga Belt that sit way up here in the top of the crust, so we're within 1, maybe 2 kilometers of the surface here. The porphyry gold deposits are forming here. And what we've been trying to understand is why nature formed these porphyry gold deposits and not porphyry copper gold deposits. So we've been focused on 2 aspects. One is the magmatic system. So we've been studying the silicate magmas that are the source or were the source of the magmatic hydrothermal ore fluids. And we've been studying the magmatic system to try and understand what the initial metal concentrations were in the silicate magma that was the source of the ore fluid. What were the initial volatile concentrations, water, carbon dioxide, sulfur in the silicate magma? What was the depth of emplacement of the magmas that evolved the ore fluids? And then what role could redox conditions have played in forming porphyry gold deposits that could be different than forming porphyry copper deposits? And then we've also been looking at the magmatic hydrothermal part of the system where the porphyry gold deposit formed. And what we're looking at here is the ore fluid composition. So what is the composition of the magmatic hydrothermal ore fluid that forms the porphyry gold deposit? How efficient is the precipitation of gold from that fluid after that fluid erupts from its source magma chamber? And then how long does it take to form a porphyry gold deposit? So this is the western margin of South America. And if we zoom in, what we can see is to the north and south, we've got porphyry copper belts. And then we have the Maricunga Belt and the El Indio Belt that are gold systems. So here on the top in red is the Maricunga Belt. And what you can see is there are several high sulfidation gold silver deposits. There are several porphyry gold deposits. And then there are 2 porphyry gold copper deposits, one of which Cerro Casale I mentioned a few minutes ago. And then to the south, we've got the El Indio Belt, where similarly what we can see are high sulfidation gold silver deposits, porphyry gold copper deposits, and porphyry copper moly deposit. So these 2 belts are unique in that they are gold rich systems, high sulfidation gold silver rich systems, and porphyry gold systems and porphyry gold copper systems. So Jose Tomas has done a lot of work logging drill core from a number of different collars here at one of these deposits, Dorado. So on the map here of the Maricunga Belt, Dorado is this deposit here just south of Lobo Marte. And he's been working with drill core and using the drill core to reconstruct the evolution of the Dorado system. And so if we look now at a schematic cross-section based on drill core logging, where the scale on the right, the red arrow, double arrow indicates about 500 meters, then what we have in the Dorado system is we have volcanic wall rocks and sedimentary rocks. And then intruded into these sedimentary and volcanic wall rocks, we have 3 porphyries, Porphyry 1, Porphyry 2, and Porphyry 3. And we also have phreatic breccias and magnetite breccias and phreatomagmatic breccias. And so what Jose Tomas has been doing is 2 things. One, he has been focused on trying to reconstruct the silicate melt composition that was the melt from which the ore fluid evolved. And to do that, he has focused on minerals that contain melt inclusions. So as an example of a silicate melt inclusion, on the left side of the screen, this is an olivine crystal. And within the olivine crystal, there are small droplets of silicate melt that are now highlighted with the red circles. And these droplets of silicate melt were melt in equilibrium with olivine when olivine was crystallizing from the silicate melt. And as olivine crystallizes and grows around small droplets of that silicate melt, it traps that silicate melt as a silicate melt inclusion shown here on the right side of the screen. So by studying silicate melt inclusions, you can reconstruct the composition of the ore fluid source magma. So Jose Tomás has been doing this in order to track the evolution of the ore forming constituents during progressive magma evolution. And he has focused on melt inclusions in plagioclase. So on the left is a representative thin section of plagioclase grains. In the center is a typical plagioclase phenocryst. And then what's highlighted here with the two black arrows, and I'll move my cursor around it, this is a silicate melt inclusion. Now, what you'll notice is that the silicate melt inclusion is not a glass. So in some systems, the silicate melt can be trapped and cooled fast enough that it goes from liquid to glass. In most porphyry systems, silicate melts, when they're trapped as inclusions, they cool more slowly, and the silicate liquid trapped as the inclusion will crystallize minerals within the inclusion. So what you get is a silicate melt inclusion that is a mixture of glass plus crystals. So if we now look at the two images on the right, top right and bottom right, what we can see are representative examples of silicate melt inclusions hosted within plagioclase phenocrysts. Now, the challenge is, how do you reconstruct the composition of the silicate melt inclusion when it was a liquid trapped in equilibrium with plagioclase? There are two ways that this can be done. One is that you can use the technique laser ablation ICP-MS, where you use a laser to drill into the plagioclase phenocryst, and the diameter of the laser is slightly larger than the silicate melt inclusion. So you drill into plagioclase plus the melt inclusion, and you extract the melt inclusion plus a small amount of the plagioclase host phenocryst. And then you can subtract the plagioclase from the melt inclusion signal to calculate the concentrations of major element oxides and copper and gold and sulfur and chlorine in the inclusion. The second way to do it is to rehomogenize the melt inclusions by heating up the plagioclase phenocrysts to magmatic temperatures. And if you heat the plagioclase phenocryst and its included melt inclusions up to temperatures of 900, 1,000 degrees, you can remelt the inclusion and then you can quench it to get a glass. So Jose Tomás has done both. And on the left here, on a typical alkali versus silica diagram, all of the blue represent rehomogenized silicate melt inclusions analyzed by electron microprobe, and all of the red represent crystallized silicate melt inclusions analyzed by laser ablation ICP-MS. And what you can see here is on the right side, on a plot of potassium versus magnesium, we can see that in general, there's a trend with differentiation from high magnesium concentrations to low magnesium concentrations, so typical evolution of a silicate melt in a calc-alkaline system, what we can see is that the potassium concentration generally increases. Now, we also are able to measure the chlorine and the sulfur concentrations in silicate melt inclusions. And shown here, chlorine versus magnesium and sulfur versus magnesium, we can also see as a function of differentiation from high magnesia to low magnesia, we can see in general decreasing chlorine and decreasing sulfur concentrations of the silicate melt during magma evolution. If we compare the chlorine concentration for the silicate melt inclusions from Dorado here on the left, you can see that the silicate melts from which the ore fluid at Dorado evolved are chlorine poor relative to Bingham Canyon magmas that produced one of the world's largest porphyry copper deposits. And similarly, the plot on the right, where we look at sulfur, the concentration of sulfur in the silicate melts at Dorado is generally lower than the concentration of sulfur in silicate melt inclusions in Bingham Canyon. But what is noticeable is the low chlorine concentration. So we've also measured copper and gold and silver. And if we look at copper, what we can see is that the concentration of copper in the Dorado porphyry gold deposits, silicate melts, it's on the low end of the copper concentration in typical Bingham Canyon porphyry copper silicate melts, but gold is very enriched. So here we have in yellow the gold concentration of silicate melts at Bingham Canyon, which is representative for porphyry copper deposits. And what we can see is that the gold concentration at Dorado is 1 to almost 2 orders of magnitude larger than the gold concentration in the silicate melts at Bingham Canyon. So one of the things that the data from the Dorado porphyry gold deposit in the Maricunga Belt indicate is that the silicate melts that evolved to form the porphyry gold deposit at Dorado were very gold rich relative to silicate melts that evolved to form porphyry copper deposits. And then if we look at silver, silver is high relative to the silver content of silicate melts in porphyry copper deposits, but it's the gold that really stands out. And then to highlight the gold content of the silicate melt inclusions from Dorado in the Maricunga Belt, they are roughly similar to, over the same range of gold concentrations in alkaline magmas, indicating a difference in the composition of the magmas that give rise to porphyry gold deposits versus porphyry copper deposits. If we look at copper, gold, and silver versus magnesium, one of the questions that we continue to ask and to try and answer is how the ore metal budgets behave during magma evolution. And so we know that the gold contents are very high relative to typical calc-alkaline porphyry copper deposits. So we're interested in trying to understand whether or not the gold enrichment occurs in the source, or if the gold enrichment occurs during the evolution of the magmas as they ascend from the lower crust to the upper crust where they exsolve the ore fluids. And so we continue to work on this. So in terms of understanding the depth of magma emplacement, on the left, we've plotted gold in parts per million or grams per ton versus the ratio of lanthanum to ytterbium. And the ratio of lanthanum to ytterbium is used as a proxy for the depth at which the magma evolved. So at what depth within the crust did the magma originate and evolve that to ultimately form the ore fluid? So now here on the left, I'm showing the data for porphyry gold plus or minus copper deposits. The gray area is the gray area for all giant porphyry copper plus or minus gold globally. And then in orange are porphyry copper moly plus or minus gold deposits. And the data from Dorado span this entire range. So we continue to work to try and interpret the data to understand what they're telling us about the evolution of the ore fluid source magma. Now, on the right is gold grade, also on the y-axis, so the same scale, y-axis on the left and the right, versus lanthanum to ytterbium. And the key again here is that high lanthanum ytterbium ratios indicate deep magma differentiation, and low lanthanum ytterbium ratios indicate shallow magma differentiation. And there are data globally from many papers, including this paper from Howe, that show gold grades are highest in that when the ore fluid originates from a magma with a low lanthanum ytterbium ratio, indicating shallow magma generation. So Jose Tomas has been trying to interpret this, and here now we've flipped to put the lanthanum ytterbium ratio on the left. So again, high lanthanum ytterbium ratios would indicate deep magma generation. Low lanthanum ytterbium ratios would indicate shallow magma differentiation. And here what we can see is that the gold porphyries in the Maricunga belt have generally low lanthanum ytterbium ratios, which would indicate rapid ascent of a deep magma to shallow levels of the crust where it evolved. So this is a work in progress, and now we're trying to understand how the source magmas for Dorado, how they could have originated in the deep crust or the subarc mantle and ascended to shallow levels very quickly. And I'll just highlight on the right that one of the things that is characteristic about the Maricunga belt are there are basalts erupted in that area that are in time equivalent basalts with porphyry gold deposits that are an indication for extension in a thick arc. And one of the suggestions is that extension in a thick arc can lead to very high gold copper ratios in magmas. So we continue to work on this. So then the second study that I'll talk about focuses on this area in blue, trying to understand how magmas generated in the subcontinental lithospheric mantle could be gold rich. And for this study, we'll move across the border from Chile to Argentina, and we'll focus on work that was led by Santiago Tessara, who was a PhD student at Universidad de Chile and is now a professor at Universidad de O'Higgins in Chile. And what Santiago focused on in one of our studies is assessing the enrichment of gold in magmas generated in the subcontinental lithospheric mantle. And so what he did is he looked at samples from epithermal veins in the Cerro Vanguardia district in Patagonia, and he focused on xenoliths erupted in the same area. So here, the map on the right, we're looking at the Deseado Massif in Argentina. All of the white dots are gold-silver epithermal deposits, and the red dots are xenolith localities. And what Santiago did is he studied the phase assemblages within these xenoliths that sample the subcontinental lithospheric mantle. So these xenoliths are really important because they are bringing up samples of the subcontinental lithospheric mantle rapidly, erupting these samples at the surface. And so they allow us to study processes happening in the subcontinental lithospheric mantle, which is the source of the magmas that ultimately form porphyry gold and porphyry copper deposits. So if we look at one of the, if we look at representative backscattered electron images from these xenoliths in the Deseado Massif, the two backscattered electron images here are general views that show you veins of interstitial glass. So we have olivine crystals on the right and on the left, and then cutting through these olivine crystals, we have a veinlet here that would have been silicate melt in the subcontinental lithospheric mantle. And if we look at these veinlets, these silicate glass veinlets that would have been silicate liquid, we can see now in the two images here, C and D, we can see that the silicate liquid that infiltrates the subcontinental lithospheric mantle, it reacts with minerals such as spinel, olivine, and clinopyroxene. And we can see here in particular in image C, we can see that the reaction of this interstitial silicate liquid with spinel, it changes the composition of the spinel at the interface between the spinel and the interstitial silicate liquid, and it also changes the composition of the silicate liquid. So if we now look at this zoomed in area E from panel B, we can see in this case, the top right and bottom left are olivine crystals, and this is a veinlet of interstitial silicate liquid. And within that veinlet, the minerals that are important are armalcolite. Armalcolite is a titanium oxide mineral that has this composition, Ti2O5. And the presence of armalcolite, that indicates that this sample and this interstitial silicate liquid, that it existed at high temperature and high pressure in the subcontinental lithospheric mantle, because armalcolite is only stable at temperatures and pressures that exist in the subcontinental lithospheric mantle. And then importantly, are crystals of apatite. So this AP is the mineral apatite, and we're highlighting here one crystal and a second crystal of apatite, and then also these nickel copper sulfides. So the armalcolite and the apatite and the nickel copper sulfides are all physically part of this interstitial silicate liquid vein that represents silicate liquid infiltrating the subcontinental lithospheric mantle. Now, as an aside, and what's important here is that my lab group over the last decade, we have also developed the ability to analyze apatite crystals for the specific presence of different oxidation states of sulfur. So we've developed an analytical method where we can determine the abundance of sulfur 6+, sulfur 4+, sulfur 1+, and sulfur 2- in apatite. And what we've been able to demonstrate is that the relative abundance of different oxidation states of sulfur changes, as shown on the right, with redox conditions that change. So at very reduced conditions of FMQ-1, almost all of the sulfur in apatite is sulfide. But as the redox conditions become more oxidized, at FMQ plus 3, almost all of the sulfur is sulfur 6+, and there is effectively 0 sulfur 2-. So we've developed a sulfur in apatite oxybarometer where we can measure the abundance of sulfur 6+ and the abundance of sulfur 2-, and then we can calculate by using the ratio on the y-axis of sulfur 6+ divided by total sulfur versus oxygen fugacity on the x-axis. We can measure the sulfur oxidation states, and then we can calculate using this curve that we developed experimentally, we can calculate what the oxidation state was at the time that apatite crystallized. So back to the samples on the left that Santiago studied from the Deseado Massif. all of these apatite grains in the mantle xenoliths, Santiago measured the abundances of sulfur 2 minus and sulfur 6 plus in every one of the apatite grains, and then calculated the ratio of sulfur 6 plus divided by sulfur 6 plus plus sulfur 2 minus, and used that sulfur 6 plus over sulfur total ratio to calculate the redox conditions during the crystallization of apatite. So we've put together a story that explains how this is important for the enrichment of magmas in gold. So the image here, panel A, here we're showing schematically all of the dark gray are peridotite wall rock. And then we have in the center here, the light gray, this is the infiltrating silicate melt. Now, the wall rock in the subcontinental lithospheric mantle has an oxidation state of about 0 to plus 0.8 above delta FMQ. Whereas the interstitial melt that percolates into the subcontinental lithospheric mantle will be more reduced. So it has an oxidation state of delta FMQ of negative 2.2 to negative 1.2. So there's a redox gradient from reduced silicate liquid to oxidized peridotite. So in a reduced silicate liquid at low oxygen fugacity, sulfur will exist as a sulfide liquid where all of the sulfur is S2 minus. We also have these crystals of our malcolite, titanium oxide, that in essence tell us the minimum pressure and temperature. And remember that this phase assemblage is being trapped in the image on the right in the subcontinental lithospheric mantle. So in essence, it's giving us an image of what's happening in the mantle at the base of the crust. So as the silicate melt infiltrates the peridotite, it will react with minerals such as olivine and spinel and pyroxene. And what we show here schematically is that iron 2 plus in the silicate liquid, it will react with and it will grow reaction rims on pre-existing ferromagnesian silicates. And this will liberate iron 3 plus. So what you have is now a change in the iron 2 plus to iron 3 plus ratio of the interstitial silicate liquid. And this causes the interstitial silicate liquid to become oxidized. So as the interstitial silicate liquid oxidizes from delta FMQ of minus 2.2 to more oxidizing conditions approaching the redox conditions of the peridotite, that will destabilize sulfide liquid, and it will oxidize some of the sulfide to sulfate. So this process will result in transformation or oxidation of sulfide 2 minus to sulfur 6 plus, which exists as this SO4 with a 2 minus charge. And during oxidation of sulfide to sulfate, the resorption of sulfide liquid will liberate metals such as gold, and that gold now becomes a dissolved component of the interstitial silicate liquid. And as a result of these processes, the interstitial silicate liquid, it is now gold rich. It is now more oxidized than it started. And this more oxidized interstitial silicate liquid, now it is enriched in gold. And this liquid, if it continues to ascend from the subcontinental lithospheric mantle into the overlying crust, where it ultimately can make its way to shallow levels of the Earth's crust, then it would be a gold-rich silicate melt that could evolve gold-rich magmatic hydrothermal fluids. So if we look at that process now on a plot of the sulfur 6 plus over sulfur total ratio on the y-axis on the left versus oxygen fugacity on the bottom, and gold concentration of the silicate melt on the right, the initial silicate melt in the subcontinental lithospheric mantle, the initial silicate melt that infiltrates the mantle peridotite is reduced. And all of the sulfur would be sulfur 2 minus. So this sulfur 6 plus over sulfur total ratio approaches 0 at reducing conditions. But as that silicate melt reacts with minerals in peridotite, olivine, spinel, pyroxene, that oxidizes the initial silicate melt from this red star to this yellow star. And that oxidation from reducing conditions to relatively, certainly much more oxidizing conditions, that's important because as the oxidation state of a silicate melt increases from reduced to oxidizing conditions, we know from experimental work shown here with this red curve that the solubility of gold in the silicate melt increases significantly. So if we use the scale on the right, the solubility of gold in a very reduced silicate liquid will be very low, so less than 1 microgram per gram, because gold at very reduced conditions will be contained within sulfide liquids. But if the silicate melt is oxidized and the sulfide liquid is resorbed, the gold is now transferred from the sulfide liquid into the silicate melt, and the concentration of gold increases from below 1 microgram per gram to now values approaching 4 micrograms per gram. So almost half an order of magnitude, or a factor of 5 increase. And this process is one process that can explain the increase in gold content of the subcontinental lithospheric mantle here at the very bottom of the magma plumbing system, where ultimately the source magmas for porphyry fluids evolve. So two sort of different but complementary research projects, one of which this work by Santiago is published. The work with Jose Toma, we're working to now finalize 2 manuscripts and submit those for publication. And with that, I will stop and take any questions.
Thank you very much, Dr. If there is any questions, the participants are allowed to leave the questions in the box chat, please. A todos los participantes, por favor, si es que hay alguna pregunta, pueden dejarla en la caja de comentarios.
And hopefully I didn't put people to sleep.
Well, there is one question. It says, Jaco says, "Hi Charles, thanks for the presentation. I usually compare the magma system with the Coke, but I think compare with the champagne is the tail. Thanks for that. But my question is, if we have a key signature in a magma system, that means that probably the deposit we could found are copper gold or gold porphyry deposits."
Wait, can you repeat that again?
Yes, I usually compare the magma system with the Coke, but I think compare with champagne is the tail. Thanks for that. But my question is, if we have a key signature in a magma system, that means that probably the deposit we could found are copper gold or gold porphyry deposits.
Yeah, I would say maybe. Yeah, I think the Attacite signature in terms of strontium yttrium ratios and other trace element compositions, there does seem to be that general correlation.
Thank you. William asks, have you ever listened about the La Colosa or rich porphyry in gold rich porphyry in Colombia?
I have heard of it, but I'm not familiar with it at all. Colosa. So no, my answer is no. I'm not familiar with that deposit.
Thank you. Goyo asks, is it possible the position of gold at more than 500 cesium grades?
I think that seems pretty high. Yeah, the fluid inclusion homogenization temperatures in the porphyry gold deposits, they generally indicate gold precipitation at lower temperatures. So it's possible that gold could precipitate at higher temperatures, but that's not what I'm familiar with by way of fluid inclusion homogenization temperatures.
Thank you. So, Goyo asks, is it possible the position of gold? I'm sorry. Kevin asks, hi Charles, thanks for the presentation. You mentioned the case of the Maricunga belt in Chile. Do you know of any example of a belt in Peru, given that in this country there are mainly copper, gold, and copper molybdenum deposits, or an example of mineral system?
Yeah, I'm not aware of a gold belt in Peru. So the El Indio and the Maricunga belts in Chile seem to be very well known, but I'm not aware of a similar belt of gold-rich porphyry and epithermal deposits in Peru.
Thank you. Jose Franco asks, hi Adam, great presentation as always. How can these studies match with those conducted in the upper part, porphyry epithermal, such as fluid inclusions for hydrothermal fluids?
So that is we are working on that. So Jose Toma characterized fluid inclusions in the quartz veins at Dorado that host the gold, native gold, and he has analyzed the fluid inclusions and is processing those data. So we're currently working to process the fluid inclusion data and then interpret those data. So we hope to publish that sometime next year.
Thank you. Emilio Torres asked, gold enrichment in barium strontium rich granites is related to SCLM?
Mm. I don't think I can answer that right now. I haven't thought about barium strontium rich granites. So I can't answer that right now.
Thank you. Osman Poma asks, what is the control of magma chamber depth? So as you mentioned, that define the top of porphyry.
So what we think is certainly the case in porphyry gold deposits is the magma chambers were very shallow when they evolved the ore fluid, shallower than porphyry copper deposits. So there have been a few studies focused entirely on reconstructing the depth of magma emplacement, and the depth of magma emplacement for porphyry gold deposits is certainly shallower than porphyry copper deposits.
Thank you. And Pasco asks, thanks for the presentation, Adam. Could you talk about formation of porphyry deposits with platinum and palladium like in Greece? Do you think it is possible in the Andes?
So I'm a little familiar with the ones in Greece. The ones I'm more familiar with are in British Columbia, which I think are similar. In British Columbia, there are alkalic porphyry deposits, porphyry copper gold deposits, that also contain high concentrations of platinum group metals, platinum and palladium. They also are enriched in other metals, including cobalt and nickel. And the alkalic porphyry systems in British Columbia are associated with intermediate magmas that formed, and the deposits formed in island arcs. So we have one person, one of the PhD students in my group is working on alkalic porphyries in an area called New Afton. And it seems that those alkalic porphyries that are PGM enriched, the ore fluids evolved from more mafic magmas than typical calc-alkaline porphyry deposits. And so the slightly more mafic composition of the source magmas can be one way to explain the PGM enrichment.
Thank you. William Pulido asks, because as a gold-rich porphyry, it describes quite well you're saying about the enrichment of a fluid oxidized in the magma and becoming in a reduced wall rock enriched. The grades in the high grade are 1.5 to 1.8 grams per ton of gold, and the deposit has lengths in the wall schist rocks with uh, 10 grams per ton gold.
Yeah, I don't know that if that's a question or a statement. I agree.
Yeah, I
Hello.
think so.
I'm so sorry. Can I make my question by the voice?
Yes.
Okay. Thank you very much, Simon, for the presentation. I just asking previously about the La Colosa, which is a now rich porphyry. Actually, it's one of the richest around the world. Not the biggest, but the richest, because it has around 1.5 grain by ton in the highest grade zone. And the wall rocks is a schist, a black schist. And it describes pretty well that you are saying in your presentation, because we have a redoxed intrusion entering into a wall rock of black schist, which is reduced. So that makes that this kind of deposit, this porphyry was so rich because the oxidized porphyry entry into a reduction zone, creating a tramp, a kind of a tramp, right?
Yep.
So outside of the porphyry rocks, I mean the igneous rocks, in the wall rocks, we have zones with more than 10 grams by ton, which is pretty rich, you know. So it happens also in another sectors in Colombia, in the named Cauca Belt, but actually the Colosa it's not in the same place of the same belt. And I had the opportunity to visit the Maricunga Belt, and of course the lithology is a little bit different, but the question is, by the erosion level, in the Chile, you have a complete system with epithermal zones, and you can see in this Maricunga Belt several deposits with the epithermal, high sulfidation, and with the porphyry below, which is pretty good. But as the wall rocks are different, most of the time, so sorry, most of the time in the school at the university, our lecturers say that the best rock for hosting a porphyry is a kind of a volcanic rock. You know what I mean? But actually here in Colombia, we have a different kind of rock which create tramps and enriching this kind of deposits. So now you are saying that it's in the lowest part of the core of the crust, actually close to the mantle, that it happens. But my question is, it cannot be a combination of that. I mean, the enrichment can be happen in the underground, deepest depth on the ground, but also in the surface, close to the surface, as it happens in La Colosa.
Absolutely, I agree. I mean, what you're describing is a very efficient deposition process. So you've got a gold-bearing fluid that flows into reduced schist, and that rapidly reduces the fluid and precipitates gold. Is that correct?
Yeah, yeah.
So yeah, I agree. That's really interesting.
By the way, thank you very much for the book that you are showing us on the screen. I
Oh.
had been enjoying the reading, and it's quite
Yeah.
good for maybe for politicians, a kind of a small reading for that, a kind of an abstract for that, because all we need is copper, and the next 10 decades we will need full of copper if we want to phase out the fossils. Also,
Yep,
this will
yep.
be impossible. Most people want an electric car, but it's not so easy. Anyways,
I agree.
if
I
a
agree. Yeah.
politician will be read something of that, we all be happy, right?
Yep. I agree.
Thank you very much.
Thank you, William. Well, there's another question from Hosbel. It says, thanks, Adam. Thanks, Adam, for the presentation. I am working on a project where I have Maricunga type veinlets on the surface with molybdenite and quartz grading 0.3 grams per ton gold and 0.1% of copper. Is there a possibility that the mineralization will improve at depth?
Maybe. So are these banded quartz veins? One of the things, and I didn't talk about it in the presentation, is that in the Maricunga type veinlets, the gold is hosted in banded quartz veinlets. And the explanation for the banded quartz veinlets is they formed by very rapid flashing of the magmatic hydrothermal fluid that precipitated a silica gel, and the silica gel crystallized to quartz. And so I'd be curious to know if the veinlets that Josvel is talking about are banded quartz veinlets identical to the Maricunga belts veinlets that I'm familiar with.
Okay, so great.
Okay, thank you, Jose, for asking. There is one last question from Boris Perez. It says, what is the hypothesis about the high gold enrichment in the Chile-Argentina deposits? Where are these porphyries generated in the context of thick crust and extension, and what is the emplacement depth of these porphyries?
So I think we can say that the porphyry golds evolved from shallow magmas. Porphyry copper evolves from slightly deeper magmas. So, porphyry gold deposits are evolving from magmas that are 2 kilometers, 1 to 2 kilometers depth, whereas porphyry copper deposits are evolving from magmas that are, 3 or 4 kilometers depth. And it seems that there seems to be good evidence in the Maricunga belt for thick crust that experiences extension. Whereas in porphyry copper systems, it seems that the magmas are ascending through crust and evolving in a compressional environment. So porphyry gold deposits seem to require compression to thicken the crust and then extension that allows for deep mantle-derived magmas to rapidly ascend and pond in the shallow crust.
Thank you, Dr. Adam. I think there is no more questions. We invite all the participants to read the papers published by Dr. Adam. I think they are very interesting. So I think we all can learn a lot about that. As we come to the conclusion of today's event, I want to take a moment to express our deepest gratitude to Dr. Adam Simon for such an insightful and engaging presentation of porphyry gold deposits, insights from Argentina, Peru. Your expertise and ability to illuminate the complexities of these deposits have enriched our understanding. Dr. Sam, your contributions today have invaluable, and we sincerely hope to have the privilege of welcome you back to another of our events in the near future.
Thank you very
Please.
much.
Yeah, thank you too. On behalf of the SEG-UCE chapter, I would like to present you with a certificate of recognition. We are sending you that further later. And to our audience, thank you for being part of this event. Your presence and engagement make these opportunities worthwhile. And we look forward to seeing you at our coming activities. Thank you once again. I don't know if Dr. Simons have some words. We are very happy to have you here today.
Yeah, well, thank you very much. I hope that people found the presentation interesting.
Then, so until next time, have a great day to everybody, and let's keep exploring the endless wonders of geology together. Thank you.
Thank you very much. Good night, everyone.
Good night.